Hey there, welcome back to Short Take 331. Today we're going to talk about machine learning and linear algebra. And this is a new series or sub-series within our Short Take 331 series where we're going to start talking a little bit about machine learning. And at its basic level, machine learning is basically about training a computer program to identify and predict patterns. And we'll see how that is done over the course of the next few videos. This is usually accomplished by artificial neural networks. And these are collections of interlinked artificial neurons. So what do we mean by an artificial neuron? So here's a depiction of, or a cartoon of what the way people think about artificial neurons. So you have a collection of inputs. Here I put them all into a vector I call x, and it has components x1 through xn. So these are going to be our input data. And there's going to be another vector we call here W of weights. These are going to be our weights, and there's going to be another number here called a bias. There's going to be a quantity called A, that is the activation of the neuron, and it's given by a function of this quantity Z. And Z itself is going to be given by the dot product between the vector W and the vector X. So W has to have as many components as X, and then we sum the bias. And so all these operations, this Z equals WX plus B that goes into the F and gives you the A, are to represent the output of this neuron. So there's some inputs, and then those get combined in this way, and that results in A, this activation. This function F here is usually called the activation function, and it may take different values and different forms. So here is a picture of what's called the rectified linear unit, ReLU or ReLU, depending how you want to say it. And then there's also another possibility which used to be used a lot more. These days this one is more popular, but now this used to be more popular years ago, and it's called the sigmoid type activation function, which takes this form like this. It's a smooth rise from 0 to 1, and it's given by this function. So f of z here would be 1 plus e to the minus z inverse of all that. So 1 over 1 plus e to the minus z. And the idea of this is that given some inputs and some weights and biases, then if the x's are such that z is very negative, then you're going to get 0. You're going to get no activation on your neuron. So A is going to tend towards 0. On the other hand, if z is very large, then on the sigmoid function, you're going to saturate towards 1, and the neuron will be activated, or you're going to get a very large value here for A if you're using this ReLU type of neuron. Now, usually you will have many neurons, and so here's what the picture would look like if you have many neurons. So you will have a bunch of inputs of size n here. I encoded all those into a vector, and I stopped using this type of description up here, x1 through xn. So now all this is encoded into a vector, and each of those vectors, or rather each that vector gets fed into each of these neurons, 1 through big N. So let's not confuse the little n with the big N. So the little n is the number of components in this vector, is how much information we have. For example, if we're given pixels of corresponding to some image, then all those pixels will be encoded into this vector. They will be linearized into that vector. Let's say the size little n then, and each of those vectors, or rather, that vector is fed into each of these neurons, 1 through big N. And each of these neurons will have an output, a1 through a sub n, given by the function, the activation function f, applied on z, the corresponding z, z1 through z sub n. So in turn, each z will respond to whatever weights and biases are given in this neuron. This other neuron will have a different set of weights and bias and a bias, and this will also have a different set of weights and a bias. And so then we can go ahead and pack all these a's into a vector. This is going to be a vector a of size big N, and that then gets is a result of applying our function f in vectorized form to a vector z. So what do we mean here by vectorized? What I mean is that the z here is a quantity that is a vector. So it's imagine that z1 through z sub n form a vector, and then apply f to each of the components of the vector. And so once you do that, then you obtain the result of a, and so a sub 1 through a sub n, big N. And so that would happen. That's what happens at each neuron. Now, how do we obtain these z's, z1 through zn? Well, we have to take the weights for each neuron. There's going to be a set of weights for neuron 1, a set of weights for neuron 2, and so on, multiplied by the input. Remember, the input is the same for all the neurons. but the weights are different for each case. And then we add the bias corresponding to each of the neurons. Now I'm doing this in vector form, and so what this allows me to do is to use a big matrix of weights. So if I have a vector for neuron 1 and a vector for neuron 2, and I need to compute the dot product of each weight with each x, then what I'm doing really is matrix vector multiplication. So you can imagine this as being a matrix of size big N by little n. This big N is the number of neurons in this set of neurons. This is going to be called a layer, by the way. And so this big N is what's called the number of neurons in the layer. And this little n, in this case, is the number of inputs coming from this vector x that has all the inputs that I want. And so it's size n. And so it makes sense then to multiply this matrix that is big N by little n. And so I obtain a vector of size big N, which I can then add to this vector of biases that I call B. So this B then contains all the biases of all these neurons in my layer. As a result, I obtain this vector Z. I can put that into my activation function, and I obtain the outputs for the whole layer all at once. So that's really where linear algebra enters the game. So I then imagine I have a collection of weights in this way. So I'm going here in rows. I have the weights of each neuron. So for neuron number 1, I have this whole set of weights. They go W11, W12, all the way to W1n. And so I can go ahead and take this row and multiply by a column vector x, and I obtain the result for Z1, which then I apply F, and I get the activation for neuron number 1, and so on and so forth, all the way to the last neuron. And so that is where we use matrix vector multiplication, and then linear algebra enters this game of implementing these neural networks. Now in practice, you will have many layers. Usually they're called hidden if they're somewhere in between your input layer and your output layer. So this is then supposed to represent the whole neural network with multiple hidden layers. You have some input that could be an image, it could be sentences, it could be all sorts of things that are encoded in some way, and they generate a vector of inputs, usually numbers, and those numbers then get processed in the way that I mentioned. So here in layer 1, you have a matrix of weights, you apply that to X, and you sum the biases for that first layer, and you obtain Z1. Z for the first layer is a vector then of Z's for the first layer. You apply your activation function F, and you obtain your output A1 from the first layer. And so now, okay, well, that gets fed into layer 2. So now layer 2 will take that output, multiply by the weights, add the biases, all that happens in layer 2, and generate these Z's that then get fed into the activation function, and I obtain the activation for that layer, the whole vector of numbers that give me the activations for each of these neurons, and so on and so forth, all the way until I get to my output layer, A sub L. Here in this process that I just described, this W1 is a matrix of size n big N by little n. X is a vector of size little n like before, and A1 and Z1 vectors are of size big N. Now here in layer 2, I'm assuming for completeness, if you want, or to show you that this is possible, that this big M is different from this big N in principle, and that could very well be. And so I have M M by N to be the size of my matrix of weights, W2. So the weights for the second layer is a matrix of size big M by big N. And here the activation for the second layer and the Z's for that second layer are both of the same size. That will always be true. They will be of size M here, and so on and so forth. So you continue along the way, however many layers you may have, until you get to the output layer, which will be of some size L, corresponding to whatever problem it is that you're trying to do, if you're trying to do a classification problem or whatever it is that you're doing. So and then if you want to express this mathematically, what's going on here is that the output layer then is the consecutive application of F and multiplication of W's by X's and W's by outputs of the previous layer, and so on and so forth, and adding of the biases. So all this is basically linear algebra and applying your function to the result. Here the result would be the result for the first layer and the result for the second layer, and you apply F and so on and so forth, and all that then results in your activation layer result a vector. So I say output layer, not activation layer. The output layer will have this activations a vector. So all these weights and biases are in principle unknown. Once you start playing with these objects, with these neural networks, weights and biases actually define what the neural network does. And the behavior of the neural network is also controlled, of course, by the function of your choice. We set up here that you can choose the activation function to be different things. And these are just two options. There are other options. I think this is one of the most popular options today, if not the most popular. And so at the most basic level, then what you have is a bunch of parameters, W, so the weights and the biases. And those weights and biases then are fit to minimize a given cost function on training data. So what that means is that you will be given some data that's going to be a part of your input layer, and then you're trying to get that data to reproduce some desired output. And that means that you need to tune your weights and biases and somehow determine them. And so somebody has to give you some data and what it corresponds to, so time input data and what the expected output is. And so if you want to encode that in your neural network, then you will assign some corresponding weights, and you will define a cost function that will tell you that when you get the wrong result, then that will have a high cost, and you try to minimize that cost then by optimizing these weights and these biases. So a whole process of optimizing these parameters is where actually the learning happens, and this is a big process. Most of the learning then or rather most of what's done with these neural networks, it happens at that stage when learning happens and when you have to optimize these parameters, and that's rather non-trivial and usually involves stochastic gradient descent, just because there's usually a very large number of parameters. So these W's then are all matrices, and these B's are vectors, and so you have a very large number of parameters. And it's basically impossible to do this, or extremely impractical at the very least, to do this with canonical gradient descent. And so you have to do something that's a little different. That's called stochastic gradient descent. We'll talk more about that in future videos. For now, I think I'll stop here. And the goal of this video is then to show you a little bit of how the linear algebra that you're learning in the first few steps when you learn matrix vector multiplication as such, enters into the arena of neural networks and artificial intelligence and machine learning. And so that's all I have for you today. I hope you find this useful or interesting. And if you did, please consider liking and subscribing to the channel. And as always, if you're looking for a tutor in physics or math in English or in Spanish, maybe I can help you. You can contact me at shorttext331@gmail.com, or you can leave a comment in the comment section below and I'll get back to you. I'll see you next time.